we are going live.
And we're live.
Maybe. It's slowly getting live. Seems we are live. Hi everyone! Welcome to the Node.js Collaborator Summit, Berlin Edition 2019. Hello again, thanks for AWS to hosting this. Hey, fantastic. A couple of things to start. Okay, it's really important that we keep this environment safe and nice, and we are gentle to our hosts, so don't make a mess. Joking. It's very important that to remember that our code of conduct is still valid. So please be respectful to each other, and if you see anything, please report to one of the usual moderator organizers. But is there anybody here? Is there anybody here from the moderation team? Hey, those hands. Fantastic. Are you okay in helping out moderation? Oh yeah. Hey.
Why don't we you all come up and
come up, please.
For those who don't know.
You see anything and
moderation.
Yeah. Hey, thank you guys. Hey, Terry. I just want to say thank you to these people that keep us all good and help out moderating our issue tracker and so on and so forth. All the rules are still valid. So if you see anything, please talk to anybody of the people you see appear on stage, more or less. And okay, have fun.
High five.
Probably not, guys. You all know these people.
Let's introduce them.
Let's introduce them. So fantastic, Rich. I thought you were sorry. That was my problem. I am Matteo. This is Rich. Fantastic restaurant. Hey, Benjamin. Oh, you're Benjamin. Nice to meet you. Journey and Dan. So, hey, welcome to Benjamin Jr. Yeah. No, we go by names.
That's how we really know each other.
It's not. Here we go. Is there a camera? So you're actually standing in front of the camera. So hey, everybody that is live streaming over there, we have something going on over there. So keep in mind that we are recording. We will be probably recording all meetings.
Can they hear us if we're not on the mic?
Hmm?
Can they hear us if we're not?
I think so. Actually better than with the mic. I think if we can speak out loud.
I'll ask an IRC. I'll find out.
Yeah, I'll find out. So we will be streaming from the main YouTube. Well, you can switch. Slide. Yeah, for that. And there is also my. Oh, okay. So no, this is nice. Okay, there's a bunch of emails and so on. So if you have any problems, you can contact us and so on. So whatever, you can find those on the replay of Node. Also, so hey, this is very important. One of the requirements for the okay, thank you. If you want to interrupt, please do, because whatever, I'm making a mess all the time. So remote participation is very important. So there was a lot of questions last times that remote participation was not very good, or more importantly, non-existent. So in the agenda, every issue every session has an issue associated with it, and we ask for a volunteer for each session to set this up, coordinate, and so on. Also control that there are questions, there are things happening, and so on. And please again try to record the video. There is a chime.aws and conf details are on the whiteboard. So for remote participation, there should be a URL or something. And if you have trouble setting this up, please contact us. We'll try to help you out because it's very important that we deliver this and help out remote people. Then I think this is all. We ask for one volunteer in each room to get this done. So when the room starts, please ask yourself. We also have name tags.
Wow.
We have name tags, so you can get your name tag. Okay.
If you want.
Hmm?
Be quiet.
Yes. So again, a big thanks to our host, AWS. Again. And now it's time for going to the agenda for today. The agenda is on GitHub. You probably are familiar with this issue. It has a bazillion amount of comments in it, so keep adding more comments. It's fine. You just notify them. Send a huge lot of emails. So first of all, we start with a couple of nice talks about new things that are happening in our world, in the Node.js world. One about promises, and the other one about WebAssembly. Then we are going to split up into different meeting rooms, which are around that corridor over there. We have 3 small meeting rooms and 1 big meeting room. So how many people are in for diagnostics? Okay. How many people are in for WebAssembly? More or less entire. How many people want to talk about docs? Water. More or less all group. Yeah. So who gets the bigger room wins? Who gets the bigger room first wins? Fantastic. Then we have lunch provided by AWS. Thank you. And then we have a bunch, some other meetings, promises. Let's talk about a little bit more, discuss a bit more about promises. The website redesign and modules. So the question from me, how many of you want to talk about modules? Nobody?
There's a slow acceptance there, right?
Nobody wants to raise their hand. I know you want to talk about modules. So how many people want to talk about promises? We're going with the promises in the meeting room, very likely. And then there is website redesign. Whoa, even yes, nice. Good. So then we have a meeting about diversity and inclusivity. So some people are interested. Then the future of streams. I am, a lot of people, a huge amount of people here. And then internationalization. Yep, fantastic. But I see a lot of some people raising your hand both for inclusivity and internationalization.
Yeah.
So,
I
amazing. After all of this, we will come back here for a little bit of a presentation for what it has been discussed. So I asked everybody, every organizer, every leader of every champion of the meetings to prepare a little bit of, or somebody else that is in the room, to prepare, I don't know, a 5-minute presentation to talk about what was discussed in the meeting.
This is at 5.
Hmm?
This is at 5. So
This is at 5.
we're
Yes.
buffering all that to the end of the day.
Yeah, and we are buffering all the discussion presented today. We have a lot of things, so it will be probably 5 minutes timed. Okay, so and I think we can give room to the first. We are a little bit early, but do you have any questions?
There's not any way to move diversity and inclusivity and internationalization and accessibility to different times?
That's actually a good question. So let's see.
Oh yeah, there's an 11 to 12:30. That's still open.
You can get that slot. Yes.
Every session has a room open.
Okay.
Every block has a
So-
room open.
Well, I mean, I'm not the one that's running either of them. I'm just the one that's being bossed.
So it's Vicky. Who is Vicky?
Zeke.
I don't think he's here yet.
Hmm?
I don't think he's here yet.
Yeah,
I don't think he's here
I'm
yet.
not here yet either, but Ben Michelle's not here for internationalization.
So if we go up,
Just move it, we'll tell them.
okay, perfect. So that was the only question. Or go up. What's the first block?
I don't think that's gonna be practical because these folks are still arriving.
Yeah.
Right.
Okay. So yeah, I don't think it's practical at this point, but we might rearrange. This is the issue. So if you see changes, it will be over here.
Rachel, the real window for you is gonna be after lunch, but that's gonna pave over website redesign. Yeah, good luck with website redesign.
I mean, I care more about diversity and internationalization than the look of the website. Plus, I can just bother you until the end later.
Can we switch maybe the website redesign with one of the two? Diversity and inclusion, maybe?
Yeah.
Yay!
Is this?
Oh, okay, the inclusivity
I-
at 11:30. Yeah.
Make sense?
Diversity inclusivity is now moved to 1:30.
Is it okay?
Well, why
Thank
don't you
you.
just move diversity up and leave the website redesign?
Oh, it's also fine. Yes, we can also do that. If it's just that.
Is there anybody who wants to go to diversity and inclusivity that also wants to be a website user? We have a couple.
Yeah, we'll take
Other things.
I need
So-
to leave at 3 and I want to go for website redesign, but if I'm the only one, I'm fine with that.
Should we switch then? Who is in favor of switching?
Yeah, okay.
Who is not? Who doesn't want it switched?
All right, so diversity inclusivity will move up to
Website
1:30.
design. Yeah. Can you do the edit? Maybe even later.
I'll do it once we bring it up to Benedict. and
Where can remote people find information about how to join the breakout session?
So we will post the issue on the so every session has an issue attached, and we will post the details in that issue. For all of you that are here, somebody of you take care of doing this. Once it's set up, whatever, instruction to remotely join, place those instructions into the issue so that remote people can join the discussion and keep monitor your laptop, whatever, for questions if you move the mic for whatever reason. So I leave the stage to Benedict and Maya that will talk about promises. If you need this, but probably not, but you decide. If they all hear, probably better not, but whatever. You can use it if you like.
Can you hear me?
And me?
Isn't it better for the stream with the mic? I'm not sure if people. Isn't it better for the stream?
So.
I can change that. So we can also use the micro. So what's better, using micro or not? Use the mic.
Yeah, I think using the mic, you'll hold the room more.
Oh, okay. So is it better for Rich? Did you check on IC? Where's Rich?
So I actually went in the next room and just pulled up the stream. It was fine without the microphone. But that's the stream. I don't know if people.
Yeah, Matteo, he was shouting. So.
I was shouting, I am a loud voice.
Okay, how about we just get Dan on stage and he does the talk?
I'll be your hype person.
Oh, wait, we got that video. Actually, I tried before and it worked, so now it no longer works. So. Okay. Do we have any computer person here who knows what to do?
It is.
Okay. Yeah, welcome. So, shall we get started already? Okay. Welcome to our talk about performance, holding on to your performance promises, which is going to be a kind of an intro to our later session that is going to be on promises specifically. My name is Benedict. I work on the VA team, and
my name is Maya. I just joined the VA team this month.
Okay, so I will do the first half of the talk, and then Maya will take over. So first of all, what do we do here? Yeah, you might have seen this presentation. It's actually awesome, although this slide maybe not so awesome for us. But so why is Gary making up all of this? Because he figured out that callback style programming is kind of you don't want to do this. So what you end up with is what we call the callback hell, and this is not the place you want to be. So I guess most of you have seen code like this, or even written code like this, and this is even the easy version that fits on the slide. So this is probably not even what you find in the code base. And with promises, what you can get is this, which is a lot more readable already. But we want to take it further, or we took it further, and so with async await.
Thank you.
My pleasure. So with async await, you can write code that looks synchronous but runs asynchronous. And that's actually the code that you want to write, ideally. I encourage you to write code like this. There are some challenges with this, which we're going to explore. Another example, a recent example, is streams. So you might have used readable stream in Node, and then if you're lucky, then it looks like this. Normally, it looks even worse. Sorry. What you want to write instead of this terrible callbacks here, and you forget the end, and you do whatever. You can do this instead, at least as of Node 10. So just write for wait off, which is using async iteration, and then your code is pretty readable compared to what we saw before. So let's talk a bit about the fundamentals of this. The way it looks in Node is kind of like this. So everything is set up on top of the operating system, of course. The operating system gives you these primitives like sockets. You can have the event loop built using poll. On top of that, we have this abstraction layer in Node that is libuv. And on top of that, there's the actual event loop, which has the set timeout, set immediate, and the sockets, and you get streams on top. And on the V8 side, or when you actually go to JavaScript, you can use promises and async await. And then when you start executing, when you're inside of your JavaScript, you basically run function calls, essentially. And the operating system bit is handled by all the operating systems that we support, which is not a lot, but enough. Then, of course, there's libuv. Then Node kind of leaks into both libuv a bit, because libuv is kind of an old thing anyways. But Node also leaks a bit into the microtask queue, which is one thing that we might want to discuss later. And the rest on top is handled by V8, or if you prefer to use Chakra Core, then it's handled by Chakra Core. But I'm not going to talk about Chakra Core today, so let's stick to V8. And the interesting bits are actually the bits when it starts from the event loop. So this is where script execution starts, and then eventually you run in JavaScript, and then you go back to the event loop. So just a brief example of how this works. Let's assume you have your main function. So this is what's on the call stack then. You call it your main function, and that might then call set timeout and schedule some callback. This is then scheduling a timer inside of Node, which remembers, okay, after time ran out, I have to run F1. Then this is gone from the call stack. Then you might have some promise in there, so you schedule another callback that ends up on what we call the microtask queue, which lives inside of V8, compared to the event loop, which lives inside of Node. And it's done. Let's say you schedule yet another one, so you put another thing onto the microtask queue, and then script execution is done. So you return from main, you go back, but you don't go back to Node immediately. But first you, then let's say the timer also ran out, so then it schedules this F1 on the event loop, not on the microtask queue. Okay, now you're done, but you're not returning to Node yet, because you need to pump the microtask queue first before you get back to Node. So then we run F2 first, which can do even more things like schedule more microtasks. Then we run F3 when we are done. And then eventually we return execution to Node, which then schedules F1 and so on. And then it goes back to the operating system waiting. So this is roughly the high-level concept. There are two queues involved, and it's important to understand the difference that microtasks, which is used for promises and async await, are handled differently than what you would schedule with set immediate or set timeout, which is handled by Node completely. As said, Node leaks into the microtask queue, which is a topic for later discussion if you're interested. If you want to know more, my colleague Jake actually has a pretty awesome presentation about this that he gave this year at JSConf Asia. It's about the browser, but in the browser it's very similar to Node. So the browser also has this distinction between the microtask queue and the actual event loop, which is handled by the browser. And he can do awesome animations that I can't, sorry. So I can only do the boring ones. Okay, so that's this. Let's go into some detail. Whenever we go to the microtask queue, we say that we tick on the microtask queue. That's why we chose, I don't know, it's a pretty bad term. When you Google tick, you find this picture. It's a tick. So one of the challenges is that this back and forth between the microtask queue and the JavaScript execution and also the interaction with the main event loop is kind of expensive. So that was the first thing where we thought, okay, we can optimize this. And in fact, we did, but not to the best result. And I want to show you why this is so hard. We have this very simple example. Unfortunately, this is really the simplest example that you can think of to illustrate the problem. And it doesn't really look simple. So what we have here is two processes that are sort of running concurrently. So one is the tick process, which just immediately ticks to the microtask queue by using a resolve promise and scheduling itself on it. And this just counts down from 10 to 0. And there's another concurrent process, which is count2, that runs from 0 to whatever number you pass in and awaits on every iteration. So this is to illustrate await versus immediately scheduling something via a promise then. And the log function is just there so that we can wait on something. Actually, the log function can be simplified. So when you have async function that doesn't have an explicit return inside, then this is not any different to just writing a normal function that returns a resolve promise with undefined. So let me give you the output of what we see when we run this in Node 8. Then you get this. So you see the ticks, and then not, then tick, then not, then log. Whereas if you run the same, so that is Node 8. And now you take the same and run it in Firefox, and you get this weird output. Which one is right? I was like, yeah, Firefox is wrong. No, apparently Firefox was right, and we were wrong. Any idea why Firefox is right here? Actually, Node 10 is also right, so we just didn't backmatch the fix, unfortunately. So if someone wants to have a PR, this is good for backmatch. Any ideas? Is this intuitive that the behavior is like this? Oh, no. Okay, I agree. But actually, when you go through the specification, then it becomes clear. So, but I'm not running you through the specification because you will all disconnect. Okay, so let's analyze the process in detail individually. So the tick process just starts by tick 10, which means we execute tick 10 just as a JavaScript function. And what it does, it creates a fulfilled promise with the value 9. So b minus 1 gives you 9. And then it calls then. So it schedules what we call, or what this spec calls, a promise reaction job that invokes tick when it's run. So then tick 10 is done. So we move on to the, or we go back to the microtask queue, then we execute this job, which invokes tick 9. And tick 9 creates a promise that is fulfilled with the value 8. And so on, you get a promise reaction job that invokes tick when it's run, tick 8, yeah, and you get the concept. So that just ticks every time that we go back to the microtask queue. Okay, so that was the easy part. So what is the thing with the await? The await is actually apparently very complicated. This is the spec text for await. I've been staring at this for yeah, so whatever. It's just okay. Let's just go through the example. So we have count2 that we invoke with 4. So and the only thing that we care about here is actually the await and the thing on which we await. So we can simplify it to just this one line and analyze how this is being run. And because the for loop just does this in, just repeats this. Okay, so the first thing that count2 does, it creates this fulfilled promise with the value undefined. Okay, that we have seen before. This promise, the spec calls it V. So for whatever reason, it's the right-hand side of the await, so it's V. When we start running await, we schedule what we call a promise resolved denable job, or the spec calls it like this. I wouldn't have called it like this. The reason for this is that await or all the promise operations actually not just work on promises, but everything that's called a thenable. So everything that has a then function, which accepts these two resolve and reject callbacks. And this is for compatibility with existing things, not promises, yeah, promise-like objects, whatever. Okay, so what this job does is when it runs, it invokes the then on the value that comes in and resolves the other promise with this value. The next thing that await does, it also sticks a promise reaction onto this promise P, which when it's executed, resumes the async function. So as soon as the await, as soon as this step of await is done, the async function is suspended, and we only resume it when the actual reaction here is run. And every promise reaction has to have a chain promise on it. This is why we create a third promise, which is called the throwaway promise. So I would give it the name T here. And I will show you why it's called the throwaway promise even. Okay, so that is await. And now we start ticking on the microtask queue. So the first thing we do is we call then on V, passing P, or passing resolving P with this, or scheduling a resolve for P with the value of V, which is what we saw before. It's a promise reaction job, and it uses internal resolve function. So when that is actually run, the promise P is resolved with the value from V. So that's just fulfilled, and the value is propagated. And we schedule so we have the promise reaction chained on or linked to P, and when we resolve it, we schedule this promise reaction, which turns into a promise reaction job. And when that is run, we finally resume the async function and also resolve the throwaway promise. As you see, nothing can be changed on the throwaway promise, so that's why it's even called the throwaway promise in the spec. And if you count, so you see 1, 2, 3 steps. So every await is at least 3 steps or 3 ticks to the microtask queue. Okay, thing to remember, every await, at least if you implement the spec step by step, is 2 additional promises and at least 3 ticks to the microtask queue, whereas if you just chain your promises, it's only 1 tick to the microtask queue. So that doesn't mean don't use await. Await has a lot of advantages to it. It's just a bit more challenging for the VM to just hide all this overhead somewhere without screwing it up, which we did. So, but we fixed it. So let's go through this example quickly. What we see here is then compared to the output, so count2 invokes log with the value 0, or it logs log 0. Then the promise resolve denable job is run, which is this next tick. Then the promise reaction job for P is run, and then the promise reaction job for T is run. So that's why you have 3 ticks in between your async function steps. Yeah, and so on. And that's the explanation why this is the right behavior and the other behavior was wrong. Okay, what did we do in Node 8? We were like, yeah, we can optimize this. So what we saw is, oh, the right-hand side of the wait is already resolved. It's even it's already fulfilled. So what's the point of even scheduling this resolve denable job? So what we did is, oh yeah, just also fulfill P and schedule the final reaction job. Yeah. And so we only get 1 tick. The problem here is, so this is faster, yeah, but it's observably wrong. So if you rely on order, then you have a hard time debugging this. So don't rely on order, maybe as well. As an additional advice, it's very fragile if you depend on this low-level order. But still, so we need to get it right and still hide the overhead. This was then necessary to remove, and if you see such a commit in V8 with these passwords inside, you already know. So like fastpath, bypassing, benchmark, and debug. Okay, so to sum it up, the scheduling is actually well defined, unless in other languages. I think, for example, .NET offers some leeway for the implementations to schedule the ticks or schedule the tasks differently, but it's not predictable. So that means you run your application in 2 different versions of .NET or even in 2 different implementations, and you get different behavior. And we don't want that. So JavaScript went exactly for the opposite and said, okay, we need to specify this strictly. Looking at it naively, the optimization potential is a bit limited, but that's actually also the interesting bit because it's challenging and it's fun. And it's apparently very easy to get wrong. As you see, we even shipped the wrong thing in Node 8. You didn't even complain, so maybe you didn't run into this, but whatever. Still, we made a lot of very significant improvements. So this is a graph that shows these promise benchmarks. So the bluebird ones, the dot speed, the parallel, written using promises and async await. And another one that I added, which is computing Fibonacci numbers using async iterators or async generators. And you can see we have sometimes like 10x improvements compared to what we had in Node 7. So we can do something. It just takes a bit of time, and we need to have tests to not screw it up. Yeah. So this throwaway promise that the spec has inside is the thing that we don't want because it's just unnecessary overhead. And yeah, I'll get Maya to explain what we're trying to do.
Yeah, well, basically the part from the spec that contains the throwaway promise is actually a big part of the whole wait function. So we really tried to spare as much of these steps as we could. So, well, we got rid of the throwaway promise, and then apparently this was observable as well, because Node has this async hooks API, which is great for observing what's happening with the async primitives. And yeah, in short, basically you can hook into the async events that are happening in Node. Like you can get notified when a promise is being created, when a promise is being before or after it's being resolved. And in these hooks, you get IDs that are supposed to identify the promise in question. And why do we want to keep these IDs consistent? Because then it's easy to reason about what is happening. You can build some kind of async context. For instance, when you fire a request, a server request, then you can track all of the events that are actually triggered by this request. So you get like a complete picture, even if they happen asynchronously. So in Node 8, this example, when we simply create, we hook into when promises are being deleted, and so we log the async IDs of the promise. This is async ID, and we log the ID of the promise that kicked this asynchronous task. In Node 8, you can see we create some promises internally, we pass their IDs, and everything is traceable. Like you can reason about which ID comes from where. And in Node 10, suddenly, first of all, we removed one of the promises, as we said, so we have one init hook less being fired. But then, what is even worse is that actually all of the promises seem to be created from the outermost context. So they all get this trigger ID of 1, which is apparently wrong. And we had an issue about this, and we tried patching on top of the optimization, but this produced even another issue. So it didn't work quite well. And yeah. So the initial implementation of basically this somehow resembles the picture that Ben showed earlier. We have the value, which is the left-hand side, the right-hand side weight. Then we create one more promise in green there, and then the throwaway promise as well. And this is the async function being called itself. So this lower part happens in the microtask queue. And what we wanted to do is basically get rid of all these switches in the yellow square. So we got rid of two closures, these JS functions that are noted there. We got rid of the throwaway promise, and we didn't need to allocate one context, which was cool. This was supposed to save performance and memory because we needed to do less scavengers in the GC. So yeah, we really had performance improvements out of these. Like these are just numbers from different commits that we had doing this optimization. And then what happened, this example that I showed you a few slides earlier, we tried reasoning about the async IDs that we get from the hooks and building a tree of them, because actually when we have execution of some asynchronous events, we can build a tree from them to reason about what is triggered by what. So initially we had these three, some of the IDs themselves are not very informative, but you can still reason about what number of levels you go when calling promises. And this was in Node 8. And then in Node 10, the tree looked slightly different because we got rid of the throwaway promise. Basically, this branch on the left was hanging now on the outermost promise. So it had a trigger ID of 1. So we lost one promise and we changed the structure of the tree. And this is with this particular simple example. We had another example when we mixed promises and async await, and unfortunately there the picture was one tree in Node 8 transforming into two trees that don't have a common root, which was apparently a problem because it was the same piece of code, so it was supposed to be traceable like a single tree, and it was not. So this was really a problem. So yeah, we can some of this procedure that you probably don't want to follow. And yeah, what is the takeaway from this short story? That we need to have tests. So we first reverted the optimization as the quickest way to fix the behavior of Node. And then we started writing tests inside Node.js, which use these async hooks because they are like the most sensitive part that gets, the most fragile part that gets broken when we break the execution of async events. So later we added more tests in V8, and yeah, we are happy to see any use cases containing promises and async await that can be turned into tests that actually exercise the how valid is the execution order that we get. So we have a plan for optimizing this again on top of the tests that we already have, and hopefully more tests will appear for this. First, we're going to use, in place of this promise reaction job, we're going to have a different type for used for async await. So we are going to differentiate between these two types of async primitives. Then, first of all, we are going to get rid of the closures and the context. Actually, this should not include the throwaway promise. So the picture is not very helpful here, but we get rid of these two JS functions in the context. which doesn't change the order of execution, it just saves memory. And then if we need the throwaway promise, we can lazily initialize it. And at last, we can also lazily initialize this initial promise if it's needed. So basically, if we have async hooks enabled, we can initialize these promises so that we have the correct order and correct behavior. And if async hooks are disabled, we can optimize this away. And yeah, we expect some performance improvements, hopefully at least as good as the ones that Benedict showed you. So we are going to spare a few locations, which is memory gain, and then the GC scavengers, which is performance gain, which is the most important part. Because yeah, currently if you start using async await or turn on async hooks as well, this really drops the performance in a way that you basically don't do this. And yeah, we want to make this usable definitely. So thanks everybody.
Thank you, Benedict, for coming. Thank you, Maya. Leave the stage to Lynn, that's going to talk a little bit about WebAssembly.
And once I get this set up, I'll bring up Luke Wagner and Phil Schneider as well. Should anything be showing up there?
I'm plugging.
Do it again.
Yeah,
it's a little bit. This is still going, by the way. Just saying, we are still recording. We are going to be just 1 minute.
Wait for a couple minutes.
Yes, let's wait for a couple. Okay. You're waiting for a couple. This is just going, by the way. So just so that you know.
Should I use the microphone?
If you have a loud voice like me, and or if you have a loud voice, you don't want to use the microphone.
Okay.
It's up to you.
Okay, I'll probably use it.
Yeah, that's good.
So we're going to talk about microtask queue and the microtask. Who owns it eventually? Right. We can always come back and really interested in the
feature all of the loops.
Right, and, we're gonna potentially be, opening up this, loading context. So, like, then we have, additional context that's responding. Right, it's one of those like, yay! Right, but especially if we're managing or who's managing that.
I told you that we should start shortly, or do you think we should start shortly, or do you think we should start in a minute, or?
You can.
Okay.
Hey everyone, get back. We are going to start.
We also have breakout rooms, so like, if you have important conversations that need to happen right now, feel free to just go wander into a room and have it there. But try to just keep noise to a minimum in here because it's making the stream harder and just, general engagement. I'll say that.
Okay, thank you.
Hey everyone, let's get started again.
Okay, everyone. So hi, I'm Lynn Clark. Thanks for coming out early, especially due to the urgent lag, to talk about WebAssembly. So WebAssembly, even though the name is WebAssembly, it's about more than just the web. It gives you a way to run code that isn't JavaScript inside of the JS engine, and it does this in a way that's both safe and fast. So this means it can be really useful for you. So in this talk, I'm going to talk through a 10-minute intro that gets everybody on the same page about how WebAssembly works. And then Luke Wagner is going to talk about a few possible ways that Node could use WebAssembly. And Till Schneiderite will talk through the toolchain for compiling and optimizing WebAssembly. And then after that, we're going to have a workshop where we can talk through more of these use cases in more detail. So we'll start with what a WebAssembly module is. So a module comes in a file that ends in .wasm, and this contains the binary code for the module, which needs to be instantiated. Currently, to create a module instance, you call WebAssembly.instantiate, or instantiate streaming is actually now the best practice. I did not update my slides for that. Apologies. The first thing that you pass in to that is the binary code from the .wasm file. That's the module code. And so you extract the binary into a buffer and pass it in, and then the engine starts compiling it down for the machine that it's running on. And this is going to happen off of the main thread. So what you get from this call is a promise that resolves once the code has been compiled, and once that module instance has been created. But the compiled module code is not the only part of the instance. So I think of the module code as kind of like an instruction book. And the instance is like a person who's trying to make something with that instruction book. But in order to make that thing, they also need raw materials. They need things that they can work with. And this is where the second parameter to WebAssembly instantiate comes in. So that's the imports object. I think of the imports object as kind of like a box of those raw materials that the instance is going to use so that it can follow the instructions to make the thing. That imports object can have 4 different kinds of imports. It can have values, and the only types that WebAssembly supports for these values right now are integers and floats. So they have to be one of those two, but this is changing as we're adding more types to WebAssembly. It can also have function closures. So this means that you can pass in JavaScript functions which WebAssembly can then call. And this is particularly useful because at the moment you can't directly interact with the DOM or JS objects from WebAssembly. So instead, to manipulate objects in JS, you pass in a JavaScript function that can interact with those objects in the way that you need, and then WebAssembly can call that. And this is changing. We'll talk more about that later. Another kind of import is memory. The concept of the memory object confuses people, so I want to go a little bit more in depth on this one. With WebAssembly, you're operating directly on memory. And to do this, WebAssembly only gives you two memory operations. You can load and you can store. And when you're doing this, you're working one memory address at a time. If you're writing in a higher level language like C or C++ and using a tool like Inscription to compile it down to WebAssembly, the tool that you use will probably add in some helper code to your .wasm file. Like it could ship down code that figures out how to marshal data between JS and Wasm. And I'll talk more about that later. Now let's look at how this memory import is created and why it is created. So I'm tipping the memory on its side so that we can see JS on the left and WebAssembly on the right working together. Your JS code can create a memory to pass in as an import, or you can have your WebAssembly module create the memory, which the engine will reflect on the JS side. And all the engine is going to do internally is create an array buffer. So that's a JavaScript object that JS has a reference to, and the engine allocates that memory to you. You tell it how much memory you're going to need, and it will create an array buffer of that size. And if you need more memory later, you can do something called growing to make that memory larger. So handling WebAssembly's memory as an array buffer, like it's an object, a JavaScript object, does a few things. Because it's a JavaScript object, that means that any JavaScript can also dig around, the JavaScript can also dig around in the bytes of this memory. And so in this way, WebAssembly and JavaScript can share memory and pass values back and forth. Instead of using a memory address, they use an array index to access each box in this memory. For example, the WebAssembly could put a string in memory. It would encode it into bytes, then put those bytes in the array, and then would return the first index, which is an integer, to JavaScript, so that JavaScript can pull the bytes out and use them. Now, most JavaScript doesn't know how to work directly with bytes, so you'll need something on the JavaScript side, like you do on the WebAssembly side, that can convert from bytes to more useful values like strings. In some browsers, you can use the text encoder and decoder APIs, or a tool like Inscription can add in JavaScript functions for encoding and decoding. So that's the first benefit of WebAssembly's memory just being a JS object, that WebAssembly and JavaScript can pass values back and forth easily. A second benefit of this WebAssembly memory just being a JavaScript object is that it prevents memory leaks. When the WebAssembly instance that's attached to goes out of scope, this whole memory array can just be garbage collected. Finally, and most importantly, it provides memory isolation. The bounds of the array provide a boundary, a limit to what the WebAssembly module can touch directly. It can directly touch the bytes that are inside this array, but it can't see anything that's outside of this array. So for example, any other JS objects that are in memory, like the global object, aren't accessible to WebAssembly. And that's really important for security. When people hear that WebAssembly gives you direct access to memory, it can make them a little nervous. They think that a malicious WebAssembly module could go in and dig around in memory that it shouldn't be able to. But whenever there's a load or a store in WebAssembly, the engine does an array bounds check to make sure that the address is inside of WebAssembly's memory. If the code tries to access an out-of-bounds address, the engine will throw in an exception. And so this protects the rest of the memory. So that is the memory import. The final type of import is related to security as well. It's called a table. Sometimes in a program, you want to be able to have a variable that points to a function, something like a callback that you can pass around. Then you can pass it into another function. And in C, these are called function pointers. The function lives in memory, and the variable, the function pointer, just points to that memory address. And if you need to later, you can point that variable to a different function. So this should be a familiar concept. In web pages and in Node, all functions are just JavaScript objects. And because they're JavaScript objects, they live in memory addresses that are outside of WebAssembly's memory. If we want to have a variable that points to one of these functions, we need to take its address, the number, and put it into our memory. But part of keeping web pages secure is keeping those memory addresses hidden, because you don't want code on the page to be able to see or manipulate the memory address. Because if there's malicious code that you're running, it can use that knowledge of where things are laid out in memory to create an exploit. For example, it could change the memory address that you have in there to point to a different memory location. Then when you try to call the function, instead, you would load whatever's in the memory address that the attacker gave to you. And this could be malicious code that was inserted into memory somehow by, for example, embedding it inside of a string. Tables make it possible to have function pointers, but in a way that is invulnerable to these kinds of attacks. So a table is an array that lives outside of WebAssembly's memory. So outside of the memory that WebAssembly has access to. And the values are references to functions. Now, internally, these references contain memory addresses, but because it's not inside WebAssembly's memory, WebAssembly can't see those addresses. It does have access to the array indexes, though. If the WebAssembly module wants to call one of these functions, it passes the index to an operation called call indirect. And that will call the function. I'm missing a slide that shows it calling the function, but basically it will go into that array index and call the function. So that's how you create an instance of a module today. There are some changes to the spec in progress, though, and those changes will make it easier to work with JavaScript and WebAssembly together. So for example, one of these changes is integration with ES modules. What's the goal of ES module integration? Today, there's an imperative JavaScript API for creating these module instances. To use a function from the module, you have to set up the request to fetch it, and manually set up its imports, manually trigger instantiation, at which point you can finally call that function that's been exported. The ES module integration proposal as a declarative API, in particular the ES module API, with this API, the request for the file, setting up imports and instantiation all happen implicitly. And this should make Wasm modules easier to instantiate. But the bigger benefit is that with this, WebAssembly modules will be able to take part in module graphs with JavaScript modules. This will make it easy for JS developers to combine functionality from WebAssembly modules and JS modules. This work is currently going through both TC39 and the WebAssembly CG. I'm championing it, so if you have any questions about it, feel free to ask me in the workshop. There's another group of spec changes that are in progress that have to do with the issue that I mentioned before, which is that WebAssembly has no direct access to the DOM or JS objects. Instead, you have to use JS function imports to manipulate these managed objects for you, or you have to marshal data between these objects and linear memory, like I talked about before. There are a few proposals in the works that will make this easier. There's the reference types proposal, which adds an AnyRef type that can represent these objects directly. There's a host bindings proposal, which will optimize these references even further so that you don't need to call through JavaScript as much. And eventually, the typed objects proposal may make it possible to create objects that JS and WebAssembly can both interact with more fully. These proposals are all currently in progress, and Luke and Till, who will be speaking next, are working on these, so you can ask them questions about those. While these are being standardized, though, you don't have to wait for the spec to be totally complete. Libraries are making it easier to interoperate between JS and WebAssembly. For example, there's a tool called Wasm BindGen, and it can automate a lot of the data marshaling that needs to happen. It figures out from function signatures how to move data from JS into linear memory and from linear memory into JS values. One last proposal that's currently in progress is integration with the browser's built-in garbage collection. So this will make support for GC languages more efficient. And both Luke and Till are also involved in the proposals around this. So you can ask them more about that in the workshop, which is coming up after the break. So now I'm going to hand it off to Luke, and he'll be talking more about how WebAssembly could be useful for Node.
And let me just get your slides going here. Actually, I don't know how the slides work. So.
Does that make sense?
Okay. What I do. Okay. Sorry, folks. Oh my
Maybe you
goodness.
got a full screen. really badly.
It's not there. If they were.
No.
Move back here and then hit present, and it should magically work.
Now you won't find window.
Okay. Okay. Let me try this one more time. Okay. Okay.
Is it the other problem that's hijacking the focus or something? Like that one there?
Maybe.
Is there a way to switch on here?
Okay, you got that.
Maximize that sucker. Okay, yeah. So how might Node.js take advantage of WebAssembly? So the first one is not that different than the rest of the web. It's just like performance. It's a way to drop in some performance. So it's good for optimizing the guts of new or existing packages that you would use. And so one kind of crisp example that you might have seen written up in a blog post was Nick Fitzgerald converted the core algorithm of his source maps package, which is really pretty popular, to Rust, and just got a big 3 or 4x speed up just by writing idiomatic Rust. And there's a lot of toolchain work that Till's, I think, going to talk about next that streamlines this whole process. So I'm not going to go into that anymore. And this is sort of symmetric with the web, and so not kind of specific to Node. Kind of a more Node-specific thing is I'm going to call portable native modules. And, well, actually, I'll call them native Wasm models to distinguish it from the first case. And the idea here is that native models can be a pain because they're ISA specific and version specific, and it's just a big problem for people. And so the idea is, well, WebAssembly is a virtual ISA. That sounds great. That should give us the portability. That should be easy, right? We'll just drop it in and switch and use that instead. Like win.
I see.
Oh, sorry. Instruction set architecture. Kind of, if we have physical ISAs like x86 or ARM, then WebAssembly is a virtual one that's supposed to run the same on all machines. So, that's the idea or the theory, but one does not simply compile a native module to Wasm and then just run it in place of a DLL. That's unfortunately not just trivially a thing you can do, because each Wasm memory is its own little address space. And Lynn explained really well how there's this whole process address space, and you can't touch most of it. You only have your own little section memory that you can mess around with. And today, native modules can reach in and just totally fluidly interact with all the rest of the memory that's in the Node process. And that means you can't just pass pointers back and forth, which is what normal native module interfaces are based on. And function pointers are even more magical. There are these indices into a table separately that holds the function pointer. So that's not going to just trivially transfer over. And lastly, WebAssembly and native code just have different APIs. WebAssembly has infinite number of registers, and its stack is in a special place of memory. And then this, C APIs can put some things in registers and some things on the native stack, and that's just good. So let's consider a brute force solution, which, spoiler, not in favor of, but it's good to consider just to say, shoot. So the goal here is I just want to recompile existing sources. Can I make that just work? And let's abandon the safety properties of Node because they're not safe today, so it's not really a regression. So let's have the Wasm memory overlay the entire process's memory to say, okay, I'm just going to cover the whole thing. And yeah, so a pointer is just the same as a linear offset in this memory because it covers the entire address space. So making all those concessions, even still, we have some remaining challenges. Like we need to hack call and direct so that it takes that index and treats it as a function pointer, just calls it. Like, yeah, jump there. And that changes Wasm semantics technically, so that'd be great to change. And also some sort of magic to hide the difference between APIs. Not as magic as hacks to make that work. Also, Wasm pointers are 32 bits. When it runs a 64-bit process, we would need to either jump ahead to Wasm, like Wasm has a Wasm 64 future ID extension in which you can opt into modules that use I64 as pointers. And it's important to recognize, technically the ISA is portable, but it's really only in the sense that like x86 is portable if you run it on an Intel chip or an ARM chip. It's still just as tied to the version and of Node and the tool chain and all the other things. So it achieves some kind of low level of portability, but not the full portability that you might want. So talk about an alternate approach. Let's not have some of those downsides. So the idea is, stick with the idea that native Wasm modules have their own isolated memory, just like Wasm modules on the web. And so that means they can't reach out, touch anything else in the process. However, Node C++ can reach in and touch the Wasm memory because it is just memory that's in the process. So you can kind of efficiently put stuff into Wasm and pull stuff out, but it's this Wasm that can't reach out and touch the Node process. And then, so this means create some new API that's designed for Wasm modules to import directly. And so some pros is that this can be very portable, completely portable, if the API is kept stable, or you have control over what is the breaking change. And this also gives you a lot tighter control of the interface of what native modules are able to touch. And I don't have personal experience. You can tell me whether Node has had this problem, but at least in Firefox, with 15 years of add-ons, they reach in and call all sorts of internal functions that you didn't expect, and then you make what seems to be an innocuous change to break something. You pass the test, but of course it breaks. And that's frustrating. So this gives you a very explicit interface. Wasm modules can only call what they're given as imports, and so you know exactly what's your API surface here. Cons, of course, you have to design this whole new API, and significant source changes may be necessary, probably necessary. And also, there's going to be some copy in-out overhead, depending on what sort of data structures and how efficiently you can get the memory into your bytes into the Wasm memory and out afterwards. There's also more questions, like what sort of API style are we talking here? One is a kind of handle file of things like kernels do, which is there's some array of resources, like the real objects that are owned by Node, and then you pass in integers to the Wasm, just kind of like we did with tables, except these are just other sorts of resources. And so they're in some just like the operating system has a table of file descriptors and passes really file descriptors system index into that. You could have that for all the things. And this is very C++ mouse running. There's integers, pass them around, and this works with the Wasm MVP, which only has integers, numbers. And the other direction is a reference type all the things. And this is like what web APIs do. When you have a resource, you just hand it out. You rely on memory safety. And this is high-level language friendly. You can take those references and stick them into objects. And if you have cycles between things, that's and you can have cycles, certainly can with the DOM. So we needed the web. But if you have cycles, garbage collector can deal with cycles. This depends on the resource types extension, which is currently, I think, being prototyped in V8, but also in SpiderMonkey. So it's coming, but it's not there yet. So that's the downside. So that's the question. I don't have a particular answer there. I think the first one might be a little more desirable. That's just a gut feeling. Another one is do we allow JS interaction with these native Wasm modules? Do we allow them to import JS and do all the things with JS like they do for like the normal, like on the web or with the normal packages environments? Well, if we keep them separate, this would allow these native Wasm modules to execute, I think, on like the native thread. If I understand right from people explaining to me, there's two different event loop threads, one that runs the JS, one that runs C++. And so if we completely decouple these native Wasm modules from JS, then they, in theory, could run just like native code on the native event loop, which gives some parallelism, and that might be good. Yeah, so, oh yeah, and lastly, if there's multiple node modules, does each one get its own memory, or do we kind of put them all into one address space? One interesting thing to observe is WebAssembly allows very cheap IPC. When one instance calls another one, you're basically switching address space at the call. And instead, if you go back and read about L4's big innovation allowed to have really cheap microkernels, it was that it had this rendezvous style synchronization, which is just basically do a function to another process. So you switch address space, you can pass all your arguments and registers, and very cheap way to call back and forth. So it'd be sort of like it's like, do we take a microkernel approach with each little node module its own thing, or do we try to put them all together? It's like they're all linked in the same process. So yeah, also a question. And lastly, a stretch goal. Could we have isomorphic Wasm modules? Kind of like there's isomorphic JS modules that run either in Node. And actually, there's 3 ways to execute here. There's in Node.js as part of the native Wasm modules, so the special case I was just talking about. In Node.js, just as part of the normal ESM module graph, the stuff that's in packages that gets mixed in with JS. It's really kind of like on the web, which also is mixed in with JS. So there's 3 different places you can be running this Wasm code, which might each potentially have a different set of APIs exposed to them. And so how might that be achieved? Well, one is an intersection. Confine these Wasm modules to the subset of web APIs that are also a node. Here is a thing that is becoming more and more a thing. Or have some abstract interface and adapter modules that adapt each one. So you have your isomorphic Wasm module with some abstract interface that is adapted to the particular APIs on that platform. So just different approaches here. Not sure which one is best. So it's also a question. So these are just some introductory thoughts. You might have guessed, and happy to discuss more later in our session today. That's it.
No waiting. Yeah, we have 5 minutes.
What are those resource types that you mentioned? You mentioned something about resource types.
Reference types. This would be an extension of the Wasm type system. You could directly hold a reference to some built-in object, like a reference to a JS object or a DOM node.
I thought it was resource.
Reference types. Sorry, yeah, might have written resource, but thinking reference. That was a good question then. Thank you.
Okay.
I guess I could just do this.
Yeah.
These 4. I guess that should work. So I'll really just quickly go through a list of tools that are emerging, and really the tooling ecosystem around WebAssembly is very much emerging. So I'll only give an overview of what is currently there and in development, and we can talk about it more in the workshop. So there are dozens, I think by now, languages in some work in progress shape of targeting WebAssembly, and the GC support reference types Luke mentioned will enable many more higher level languages that currently have to bring their own GC or are just having a hard time in WebAssembly and the LPP. But I guess for this crowd, the Rust and most probably C++ are probably most common. There are the 3 most important tool chains are Emscripten, which started this all way before WebAssembly was a thing, way before Async.js was a thing, compiled to a subset of JavaScript without any specific optimizations, just one that worked really well in the browser back then already. Then there's the native LLVM backend, which I guess in theory can just compile all LLVM languages to WebAssembly. I don't think it works quite for absolutely all languages. Emscripten itself is in the process of switching to that native backend. And then there's Binarian, which is sort of this optimizing toolchain, but also part of what we expect a lot of compiler front ends to use to really target optimized WebAssembly and use that as their backend from some intermediate language. So you want to integrate your WebAssembly modules with JavaScript, and Lynn explained a bit about why that isn't trivial. And so right now you can do it manually by just marshalling it out from the linear memory. Then there's mscriptons, mbind, and Wasm bindgen, and there are a few similar tools along those lines that automatically create a JS facade in front of the WebAssembly module. And Wasm bindgen in particular makes it look like it's just a JavaScript module with a bit of a peculiar API because it's not garbage collected. So you have to ensure that you're not dealing with dangling pointers essentially. The internal data structure represented by a JS object might have been freed in the linear memory, and now you're reading out garbage data. So there are API peculiarities about it. So you went through all this, you compiled your code. Now you want to optimize it, debug it, obviously, and eventually deploy it. Debugging in browser is coming slowly. It's step-through debugging works in some shape or form in browser debugger. I honestly don't know what the exact state in the Chrome debugger most relevant to use right now, but I know that there is heavy work in progress on getting the support. Currently based on source maps, but there is a working group spinning up for adding better debug info to WebAssembly modules so that you eventually will have an on-par experience in debugging WebAssembly combined with JS, because this is crucial. You, except for fairly special cases, you want to really debug your WebAssembly modules in concert with your JS code instead of using LLDB or GDB with some connection. You want to be able to step through a JS function call, calling into WebAssembly, and that being recursive or repetitive. So standardization work that is happening. Analyzing, optimizing WebAssembly. I mentioned Binarian before, but Binarian can also be used as a standalone tool to applying a lot of general and WebAssembly specific optimizations to code, and in many cases leading to significant other speedups and or size optimization. There's Twiggy, which Nick Fitzgerald developed in the source maps work that you mentioned, that is a size profiler. Really allows you to see, okay, this is where the size of the file comes from. Wasm to allow you to have a more human, somewhat more human readable version of Wasm file. Wasm snip for just saying, I know this isn't called, so just remove it from the file and throw an exception, just abort WebAssembly execution if it ends up being called. WebAssembly Studio is this online playground where a lot of these tools actually, all of these tools are actually integrated, so you can really play around, see what happens if I apply this optimization, and you can write snippets of WebAssembly code in C, C++, Rust, and then publishing Wasm modules. You can either do that manually, compile them, package them up however you want, put them on APM, or you can, at least if you're running Rust, and this will be generalized for other languages in the future, use Wasm Pack, which Ashley Williams created. So she really streamlined this process. You install this tool, initialize it on your source project, and then you can just publish to NPM a nicely packaged thing that you can just add to your package JSON as a dependency and then use it. And then one thing that I don't have a slide on is bundler support. Webpack and Parcel both have pretty decent support for WebAssembly nowadays. And so you can, for bundled projects, you can really nicely just use WebAssembly and don't have to worry about building manually. And we should talk about all this more in the workshop. Thanks.
Thank you, Lynn. Thank you, folks. Thank you for coming. Now it's about time for a break. So I remember there are a bunch of sessions that are starting that I completely forgot which. Oh, you have the laptop. Fantastic, Dan. Thank you.
What sessions are coming up?
So there is diagnostics. There is WebAssembly. So how many people want to talk about WebAssembly after the fantastic talk? Hey, yeah, probably there is the biggest breakout room. It's at the bottom on the right. And we are doing a little bit of a break, like, I don't know, 20 minutes, half an hour, whatever. It's probably going to start
half an hour.
Half an hour. We are going to start at 11, but if you just want to go there and start setting up the live streaming and then so on, so the remote participants. Oh, name tags. There are name tags.
So get yourself a name tag.
Name tags. Hey.
Also, for those of you streaming at home, we are setting up names for each one of the breakout rooms. Those will be posted online. So, you at home, hey, we'll make sure that you're still included. We're really glad that you joined us today. Thank you. You're like an MTV host. Yeah. Hey, welcome to Hardcore Node Monsters Day. Come on.